Hear me? Yeah, I can hear me myself well. Hi everyone. Hopefully you have a nice lunch break. So I'm going to share some of our recent work on federated, like how to do rigorous conformal prediction in the federated learning setting. So this is a joint work. This work is co-led by Charlie and his advisor Ramesh, and joint work with Praneeth and Mike here. We also have here is a paper link, and we also have the GitHub repo online. Feel free to play with the code. Cool, here is the outline for this talk. So I will briefly mention why we need uncertain quantification, as several speakers already talked about earlier this morning. And I will give a brief overview of basically a 5 minutes introduction to what is conformal prediction, and then go to our method, how to do conformal prediction in the federated learning setting, and show a few like experimental results. In the end, I will conclude with a few like future directions. By the way, I think actually several speakers in the room, they also working on similar topics. Eric has a paper on label shift of in the federated learning setting do the conformal prediction, and Jashri with Charlie also have some very early work on the evaluating conformal prediction in the federated learning setting. Cool, it's a very exciting direction to work on. Cool. So before we go, like let's first start like recap the setup of the federated learning like scenario. So I will quickly go through. Suppose we have capital K number of clients, and every client we want to minimize. In front of each client, we have like weight in front of each client, and the standard or most of the FL algorithms are focusing on like how to learn a good predictive model from these collectively from all the like capital K number of clients. So given this F hat, like this predictive model learned, what we can, like what usually people do is given this test input X and go through this model and get the output, which is F hat X. And then just like as a lot of deep learning models are like operated, like just take the argmax of the output and then make the prediction, which here is a point prediction, which is a dog. So what's missing here? So as Mike alluded earlier this morning, and Alan also talked about the uncertain quantification. So in the classical like statistical learning or like statistics, instead of just to give a point prediction, you also want to give an interval, so a confidence interval. So at the first row, I'm showing a few like regression examples. Instead of just predicting what the F hat is, you also, at each point, you want to give a confidence interval, say how likely this prediction will lie in this band. And the second row, I'm borrowing some slides from Anastasia's, is for prediction like the classification problems. Instead of just give a point prediction which class this image is, you also want to give a set instead of just a 1 point. So how do we modify the current pipeline to make the output to be more like, could provide some nice uncertain quantifications overall for this pipeline? So from the previous one, instead of give a point prediction, we can give a prediction set. This C capital hat C, this function is a set valued function given input X. It will output like a subset of the like possible output space Y. So what's nice about this is, or what's nice about conformal prediction is, whatever the black box model, like it could be like arbitrary, like either from linear regression to like say deep neural networks, and regardless of what's the data distribution, you can build some types of rigorous uncertainty using conformal prediction to like make your predictions or make the model predictions to be more reliable. So that's the motivation part. I will go give a very brief overview of what conformal prediction is. So this talk, for simplicity, I will focus on like the split conformal. There's different variants of conformal prediction. So here, suppose we have a training data set D1. We use D1 to train our model, just whatever the favorite model you want. And given the f hat, we use another data set, say the calibration data set, D2. Given D2, we, together with this point predictor, we can use conformal prediction to get a set value like a predictor, which is C hat alpha. I will introduce what kind of guarantees this C hat alpha could have. So just set up the notations a little bit. So given a distribution P, we can sample n number of data points, n number of data pairs, xi, yi, and suppose we consider the classification regime. We have a capital L number of classes, which denoted by this capital Y. And what conformal prediction could provide is, given we can construct a set valued function, which is C hat alpha. Given, suppose we have an IID pair in the future, xn plus 1 and yn plus 1. Suppose that's a test data point sampled. And then what C hat alpha have this guarantee is, the C hat alpha, given this xn plus 1, it will provide a set. And the actual label will belong to this set with high probability. So basically, this alpha is some parameter you can set. For example, you can put alpha as 0.01. Then suppose you have a reasonable large number of calibration data points. Suppose small n is 1,000. Then you could, by learning this or constructing this C hat alpha, you can get a reasonably pretty good calibrated predictor that such that with high probability you will provide a prediction set, and the actual label belongs to this set. So that is what conformal prediction could have. And the nice thing of conformal prediction is you don't need to assume or make assumptions on the data distribution nor on the predicted model. So the model could be arbitrary and the data distribution could be arbitrary. And it also has a finite sample guarantee. So basically, the number of samples you have, the small n, if n is 1,000, you can treat this small error term to be super small. So that's the nice part. And I will work through a very simple example how you can construct such conformal prediction predictors. So given n number of samples, we can construct a score function which is S. Here we are taking the LAC, which is an algorithm in CP. We just take the yi's coordinate from this probability vector and 1 minus this value. And then we can compute this value for each sample. And then we compute the quantile of the n number of scores. After that, after computing the quantile, which is Q hat, then we will use this Q hat for future predictions. So basically, suppose I have an X test sample, I just evaluate each label, each small y label, whether this label together with this function is below this Q hat, and then I will construct a set which contain all the y's that is smaller than this value. And I just give a very one-page picture proof why this works. So the assumption is IID or the data are exchangeable. So suppose I have n number of values. What you want to do is you compute the quantile of these n number of values. There's a correction term here, and suppose yn plus 1, which is the score, is exchangeable to all the previous n number of data points. Then it's very likely this will lie into this 1 minus alpha fraction, that it will give you the correction prediction set. And this is borrowed from Ryan Shini's slides. Okay, cool. And how do we evaluate whether the conformal predictor, the performance? The first thing is whether this conformal predictor could give you the set that actually cover your actual label, which we refer to as a coverage. And the second one is the efficiency, because you can always construct like a prediction set that whatever x you give, I just output a whole white space. And that does not make like much sense. You want to make the prediction set to be as small as possible. So these are the two criterion that to evaluate how CP is. And for more examples, not only the classification problems, it can be applied to a wide range of problems. Yeah, I highly recommend to go to Anastasia's and Steven's tutorial on what kind of applications this conformal prediction could be applied to. And next, I will introduce how we construct this federated conformal predictor. So first of all, we have, suppose we have still capital K number of clients, and we use these to train a model F hat. And we consider for each client, we have nk, small nk number of data points from this particular client. And then the test distribution we are considering is a mixture of from P1 to PK. So the test distribution we denoted by this Q lambda, basically is a linear or this lambda is lying in the simplex. It's a linear combination of the Q test is a linear combination from P1 to P capital K. And we are considering a test data point sampled from this mixture. And given these data points from this capital K number of clients, we want to build a conformal model that works for this Q-test distribution in the future. So the overall goal is, given nk number of data points sampled from each client, we have capital N number of calibration points collected from all the clients. And then our goal is try to build a set value function, a conformal predictor, such that still achieve similar coverage guarantees as we saw before in the centralized case. So what's the challenging, or what's the challenges here? Why can't we just directly apply the standard conformal prediction techniques in this scenario? So the first challenge is, in the previous slides, I showed there's some IID assumptions. So basically, you assume the n+1 data points are exchangeable to each other. However, here you can think within each client, the data points are exchangeable, but across the clients is not that exchangeable. Consider one patient probably could go to multiple hospitals at the same time is highly correlated, so you cannot actually make the exchangeable assumption across the clients, or putting this capital N number of data points together is not exchangeable at all, or is not exchangeable anymore. So the second challenge is data heterogeneity. So basically, because there's also optimization happening here, so you cannot actually take one client's data to construct a conformal predictor and apply it to everyone else. So here in the left, we show that if you do that, you actually got some under coverage. Your desired coverage is 0.8, but then your actual coverage is way below 0.8. So also there's a heterogeneity effect, if your model not optimized pretty well, so you have very large prediction set size, which makes the conformal prediction not that effective. So how we deal with the challenges here? So we first identify what's the right assumption under this scenario. So here we are making the assumption that the data points basically essentially are partial exchangeable. So what do I mean by this? So given the test data point, we are assuming the density function can be decomposed by a mixture of k number of density functions, and lambda k is the lambda we used in the previous slides. And here you can think that instead of exchangeable across all the data points, that within each group or within each clients, the data points are exchangeable. So it's kind of partial exchangeable. And by leveraging this, figure out what's the right assumption, we actually could build the conformal prediction relatively easy. So basically, we compute the Q hat, as that n plus k multiplied with 1 minus alpha quantile. So after selecting what's the right quantile value, we can construct this distributed conformal predictor that satisfies this nice coverage guarantee. And on the right-hand side, it's slightly different from the right term, the term we saw in the centralized case. And if we set k equals to 1, then we can reduce to the centralized case. And the pipeline is we have a prediction model, and then we can apply this FCP to wrap up our model as a conformal model. And during the test, we can predict what's the prediction set for this particular test sample. And besides the setting I described earlier, we also have several extensions, like what happens if your lambda is shifted from the one you specified, as well as suppose the Q hat cannot be computed exactly, suppose it's approximated, or if we're adding some Laplacian noise to get some privacy guarantees, those can make the Q hat not accurate. We also covered those settings, but I will skip for this talk. And let me quickly go through some evaluations. So here we saw that we can actually build some conformal predictors with nice coverage guarantees. And we also found that the optimization algorithms you applied really matters a lot in this setting. So basically, the more accurate the model is, the better the smaller the set is, or the better the conformal prediction model is. And actually, our previous, more like an advertisement for our previous algorithm called train convex and train. I joint work with Praneeth and Mike last year's NeurIPS. This is more like convex-fied approach, try to tackle the data heterogeneity challenges. And this conformal prediction algorithm could also be applied to do more some other applications like selective classification. So basically, suppose the prediction set size is small, then it is more likely to be accurate. So if we pick the predictions or make more accurate predictions by just making predictions on those with small set size, then we have pretty high accuracy. And then if we don't do the selective prediction, the accuracy is pretty bad. And the last one is we can also use the set size to compute whether, basically the larger the set size is, the predictions are more likely to be inaccurate. So this is a relationship between the accuracy and the set size. So larger, the worse accuracy. So that's all the experiments and evaluations. We have more results in our paper. Feel free to check that. And some future directions, which is quite related to today's earlier talks. First one is how to do more personalized conformal predictions. So here we are more considering a centralized model, how we deal with the future data points sampled from the same distribution, how to adapt to each client. The second one is suppose a new client joined and the client distribution is also shifted from the previous ones. And the last one is how try to extend this framework to more complex tasks like segmentation, multi-label classification, detection, all kinds of applications there. So I will stop here, and thank you.
Any quick questions while short-term setup? Please go ahead.
Maybe it's good to.
Okay. Thanks, Yaodong.